Hello. Hi, everyone. First of all, I want to thanks to organizers for this opportunity. Well, in this talk, we refer to the thermodynamic consequence for the modified raster gravity. This work was developed joint with Karen Bruce. If you have questions or some comments about this work, please, this is our email here. And this UFLAS is referred to the Universidade Federal de Lavras. This is the University of the Physics Department of UFLA in Lavras, Brazil. Well, we will study thermodynamic aspects of the modified raster gravity. This modified raster gravity, we proposed it recently. In this context, we shared the non-conservation of the energy momentum tensor and developed all the formalism of thermodynamics for this case. Well, first of all, we know that the general relativity has been successful tested with observational data. However, there are some observational data it does not explain very well. For example, the dark matter and the acceleration of the expansion of the universe are very interesting problems that is not possible to have some answers using only the general relativity. And also, when there are not a complete consistent theory of quantum gravity, perhaps the loop quantum gravity steps some way in order to quantize the gravity. However, there are some little problems that is necessary to understand better the gravity. Then there are modified theories of gravity that try to answer these problems. One of them is, for example, the non-conservation of the energy moment. This idea was developed by Russell in 1972. And in that work, the conservation law is questioned. This is a very interesting step. However, this theory of gravitation, is not based in the Lagrangian theory, for example. And essentially, there are some steps in order to find the field equation using a Lagrangian formalism. In this work, we present some Lagrangian formalism that is like raster field equation, and in the order that the energy momentum tensor is not conserved. In this case, is similar to the Russell theory gravity. In this context, we will analyze the first and the second laws of thermodynamics, and we will present first steps in the context of the cosmology, and we show that these equations for the gravity obtained from the Lagrangian formalism will be a very interesting steps in order to understand the gravity. Well, the field theory is given for this action. This is the curvature of the standard theory of gravity of Einstein. Here is this curvature is coupled with a field vector. This field vector will be the more important field in order to modify the gravity. And there are and this field is constrained by this part of the action. The Zassar-like gravity theory is given for this equation. This equation, when delta and beta, delta beta will be 0, we obtain the Einstein gravity. In addition with this equation, we have the current equation. This current equation is for obtaining the field, these field vectors, and we need to identify. Later we will talk about this. The conservation law for this theory is given for this equation. This equation is similar to the Rastahl equation without these parts of the equation. This equation is similar to the Zassar equation. And this is a modification given for the field vectors xi in this case. More about this equation, field equation for this modified gravity is we will talk in another context, in other work parallel with this work. The thermodynamic aspect we will use for the rest of this work, energy moment of the tensor of a perfect fluid, a simple fluid. And we coupled this to the Rastahl gravity using the Lagrangian matter. Rho is the density of the energy, P is the pressure, isotropic pressure, and this BA is the velocity of the fluid. This is a time-like vector. And this HEV is the orthogonal projection to the space orthogonal to the for velocity. Well, this energy momentum tensor is, we consider the thermodynamics, is necessary to complete with macroscopic variables. These macroscopic variables we consider in this work are the energy momentum tensor, given for, we described it above, and the flux of particles, given for this in a vector, and the flux vector for the entropy is given for this A vector. All of these macroscopic variables is defined in this way. The perfect fluid, the number of particles, is the density of particles, and this sigma is the specific entropy per particle. Well, all of these macroscopic variables satisfies a thermodynamical equilibrium, like the conservation stress tensor, the conservation of the number of particles, and the second layer of thermodynamics given for this equation here. In this case, the current of the particles is possible to have a particle source or a sink of the particles. The thing also in the case this equality will be zero, we will have a conservation of the number of particles. Here is the second law of thermodynamics given for this equation. In addition of this equilibrium thermodynamics for these macroscopic variables, we will need to consider the Euler equation given for this equation and the Gibbs-Duncan equation given for this. All of these laws, including these two equations, will complete the thermodynamic aspects in covariant form in the context of relativity. And in the next, we will develop this equation in order to satisfy the non-conservation of the stress tensor energy given for this kind of equation given for the last like gravity. For this, it's necessary to complete all the field equations, and we will assume a very strong assumptions given for the vector field C. We will assume that this is related with the force velocity of the fluid given for this equation. This is a strong assumption, but we will be that this assumption is naturally true in this context, especially in the context of cosmology. In this case, of course, the energy conservation law in terms of this assumption is possible to rewrite in this way. After that, this equation will project along the velocity, and we will obtain this equation here. And in the case of perfect fluids that described above, it's possible to have this result, where here is lambda is this is this variable lambda, and p is given for the pressure more this additional part is given for the curvature too. This is in the case that lambda, for example, will be 0 and delta 0. In this case, we will obtain the equation for a standard cosmology. The conservation law for the particles in this context is given for this equation. In the case of this flux of current will be 0, the current particles will be 0, we will have the standard equation for the conservation of the particles. And in this case, by using the Gibbs-Duncan equation and the Euler equation, we obtain this relation for the second law of thermodynamics, a covariant thermodynamics for Russell theory. This is given for this equation. Well, because there are many variables here, we will restrict only in 3 assumptions. These assumptions is related with the current of particles here. We will choose adequate choose for this current in order to try to solve this equation in the context of the cosmology? Well, these three possibilities is given for the current of particles. We will assume here that the current particles will be zero, will be this equation and this equation. What is the interesting for this choose? In the first case, we will consider number of particles is conserved, the conservation of the particles, and the flux of the entropy is increased in this case. This is interesting because the universe will have an increase of the entropy. It's not adiabatic in this case. In these two cases, we will assume that the current of particles is given by this equation. In this case, the entropy will be zero. In this case, we will prove that the entropy, the universe, for example, when we applied this choose in the cosmology context, we will will have that the universe will adiabatically expansions. But we will have a production of the particles. This is a very interesting observation here. In this case, we will have the increase or decrease the current of particles and the entropy. We will impose also that it will be zero or will increase in the expansion of the universe, for example. In addition, with this, we will consider the temperature, the evolution of the temperature too. For this, we need to assume that the density energy is an exact differential and depends on the temperature and the number of particles in this way. When we accept this assumption and using of course the low conservation of the energy and the particles and the Gibbs-Duncan equation, it's possible to find this relation for the temperature. And we will specialize this temperature, this equation, for the three cases assuming above for the current equation. And the first case is possible to, for example, when the current of particles is zero, it's possible to obtain the part for this equation, to obtain this relation for the temperature. This relationship we will use later or in the case of the cosmology. The second case for the current is possible to show that the temperature will be this relationship very easy, more or less very easy. This is a adiabatic system, but there are a production of particles in this case. And for use in this equation, we will have also how the temperature is the behavior of the temperature in the time, for example, for the cosmology. In this and the third case also, we will have the same temperature law, and the particles will be constant. The entropy of the specific entropy of the particles will be constant, and also we will have the entropy is related with the particles production in the universe of in this case of the Zastal theory. Well, now the part for the cosmology, we will suppose that the space-time of the cosmology is given by this metric. In the rest of the work, we will assume that the spatial curvature will be 0 here, and we will use the standard cosmology. When use the field equation for the raster-like gravity, we will obtain this equation for rho p, and the conservation law is given here. And p, in this case, is given for the pressure, more all of these variables here, and gamma is given for this. In order to solve this equation, because the complexity of this is possible to do that. However, we try to see that is similar, in which way is similar this cosmology for the standard cosmology. And we will assume two types or two space times for A, for the parameter A here. We will assume that this is a potential and exponential behavior, and that kind of solution satisfies all of this equation in this way. We will assume first the equation of state, the relationship between the energy density and the pressure is given for this equation. In this case, omega is a constant. In the first, for the first case above, that for the current, in the three cases that analyzed above, we have the following results. For the density of energy, we obtain this equation. For the parameter is given for this equation. All of this equation, when we have the limit of general relativity given for delta equal to 0 and beta equal to 0, we will obtain the standard gravity, the standard cosmology with the delta for the radiation. And then we will have here, in these cases, the behavior of the number of particles and the entropy per particles given for this relationship. And this is interesting, because the non-conservation of the energy in this kind of gravity, raster gravity, is this field equation can explain the entropy production in the universe. Of course, when we have suitable parameters here. For the second case of the current particles, we will have this relation. Of course, the number of particles increase, and this is adiabatic. This that I mentioned it before. The entropy is 0, is another adiabatic production of particles is in this case obtained. And finally, the third case is similar to the second case. However, in this case, we will have a variation of the energy, density of energy, and the number of the particles is given for this equation. And of course, is another adiabatic production of particles with production of matter. This is also very interesting behavior of this cosmology. in this case. Well, this is, we present here preliminary results. In this case, it's necessary to compare these results in order to link these constants that appear here and here with the data. However, the main results of this using this theory is very interesting because we will have a curvature evolution will be compatible with the adiabatic condition of this this work, of this context, and we will have a production of entropy and particles during all the production, all the process. And when the curvature decay adiabatically, and using the state equation, the standard state equation between the density energy and pressure, the temperature law is given for this equation. In the case this omega is one part of 3 part 1, it's deduced for this equation that is the usual Planck spectrum, generally cited for the adiabatic photon production by Lima in the paper of Lima. But we will generalize this in the case of this context of the Rastal theory. And finally, this kind of particle of theory of Rastal-like theory for gravity is interesting that we will have a matter of particle production in very different cases of thermodynamical aspects that is usually given for the evolution of the universe. Well, thank you very much for your attention. There are some references here. Here we have a Lagrangian also in the cosmology in the cosmology context, one formulation of the Lagrangian Rastal theory, and this will public the next days the Lagrangian formalism for the Rastal-like theory, where we develop it in more details the action present in this work. Thank you very much for your attention.